Hi everyone. Welcome to the CSP seminar this week. So this week is our great pleasure to have our new colleague, Professor Vladimir Dvorkin, to give us a talk. Professor Dvorkin joined us starting from this semester, and it's my great pleasure that we work together to teach a course on optimization for signal processing and machine learning. Prior to Michigan, Dr. Dvorkin worked as postdoc at MIT, and before that, he did a PhD at Technical University of Denmark. Right? So in this talk, he will talk about something interesting on formal privacy guarantees for optimization data sets in power system. So welcome.
Thank you, Chin, for giving me this opportunity to present my work on privacy, optimization, and how it helps to improve decision-making in power systems. So we have a very private setting to discuss privacy, which can be better. We will start by, overviewing power systems. Okay, power systems. So this is the main object of my research, and traditional conventional power systems looks something like this. We have a high voltage grid that has conventional sources of power generation, such as nuclear generation, natural gas-fired power generation. And producing this power, it's transmitted to points of consumption, and then it goes to us, to end consumers of electricity through the distribution feeders with high medium voltage distribution feeders. This operations power system is guided by optimization, and here we can see every component of the power system as a small optimization task. For example, we need to optimize conventional generation. We need to optimize allocation of energy to meet transmission constraints. We also need to optimize distribution feeder operations by using local generation or some emergency resources when needed. Power systems of the future look different. So we see that a lot of conventional generation displaced by renewables. On a distribution feeder level, we also have a high penetration of utility scale PV generation, and conventional means of backup power is displaced by energy storage units. Consumers are also different. They have electrical vehicles, energy storage, and smart devices to optimize their electricity bills. We also have a new type of customers, such as data centers, and so on and so forth. So the grid is evolves, and we see this grid as a collection of small and big optimization problems. Typical problem is called power resource allocation problem. So what we are doing, we gathering information about the cost of generation from different resources, and we plug it into one optimization problem that also enforces grid constraints, generation constraints, and we obtain the cost optimal solution for energy dispatch. So we enable least cost and reliable power supply by solving an optimization problem. And depending on the context, it can be linear programming, it can be quadratic programming, or other forms, NLPs and other forms. Another typical problem is to predicting weather-dependent resources. So we have solar generation, we have wind generation that depends on the weather. So we would like to leverage historical records of this generation, some ARIMA models, or we can use turbine models in order to map weather forecast into power generation. Would also solve optimization for that. Another typical problem is demand response. The idea is that using all the smart devices at home, we can help the grid to meet high penetrations of renewables when the grid needs it. For that, we would receive a signal, or we'll coordinate with grid operator to figure out the optimal timing of our consumption. And with a new type of generation, like the, consumers like data centers, we can also decide on optimal siting of our electricity consumption. Say this is a network of connected data centers, and we like to train some large language model we would strategically coordinate with system operators on what part of the grid to place such energy-intensive job. What we know about optimization on real data, that often this information will be revealed a result in our optimization results, right? If we abstract for a moment and think of some general problem like quadratic programming for resource allocation problem, what we know about this problem, that solution will always lie at the boundary of feasible region, meaning that when we will have a change in the feasible region, this change will be exposed through the optimal solution. So we also have a case of regression analysis. Say we have a distributional shift, we have all this information can be leaked through the updated regression weights. We also have classification problems where we say we like to classify operating point as stable or not for power grid. We would train a classifier that will separate the points that belongs to two different classes, like stable or non-stable. And what we know that our classification rule will be sensitive to the boundary points. So if there was a new data point included in the data set, it will all can be exposed through the optimal result. If we zoom into specific problems in power systems, cases of power systems, so we will see that a lot of information about optimization results in power systems revealed to public. At any point in time, you can go and see how electricity prices look like for this grid, which is New York Independent System Operator. And you can already, you don't know much about the system. You might know some aggregated topology, but you don't know the parameters of the lines, you don't know the parameters of the loads, but the prices that are displayed here, they can already tell you much about what's going on in the system. For example, in the areas with high prices, we can reason about congestion in the network, right? We can also reason about the level of load, or also the cost of generation in the system. These parameters never been explicitly disclosed, but you can reason about them just observing the optimal solution to our usage problem. We also, let's confirm with this. In a medium or low voltage grid, distribution system operators collect information about the load of customers. And when we think about customers, they all have their own electric signature. So that will describe their consumption. So it can be some high frequency component, smaller frequency component. This information is never explicitly disclosed, but when a system operator would release some voltage measurements, that is not the private data per se, all this information will be leaked through the voltage release. So this is all poses privacy risks, right? Although we don't explicitly share the data, this data leaks through the optimal solution to our problem. Power systems is also very special infrastructure systems because this is a crucial infrastructure. And for the reasons of national security, a lot of information is kept private. So and when you think of agents that engage with the system, like generators or consumers, so they don't know exactly the system that they are engaged with, right? Just to give you an example, here we have a standard IEEE 118 bus system, and we like to solve a dispatch problem for 1 hour of the day. Right? The file of data that collects all necessary data to solve this problem includes 1,079 rows, right? Here on the system, you see a lot of participants like loads or generators, right? Given depicted by voltage sources. So every generator here owns only 2 rows out of more than 1,000 rows in the data set, right? And this is basically how much the generator knows about the system. They can be side knowledge, they can be some general understanding of the system, but specific parameters of transmission line, specific parameters of load consumption is not available to a generator. So you kind of engage with a black box and you're hoping for the bad outcome. So you can really compare it with some stroll in the fog, right? You can move in a fog, but you don't really know how far you can go, right? What obstacle you will see. So in today's talk, motivated by all this problem, I want to discuss 2 specific problems the intersection of algorithmic privacy and optimization as applicable to power systems. In the first kind of problem, I will talk about privacy-preserving optimization. That such optimization that takes optimization data as input, produces the optimal solution, but at the same time, we have a formal guarantee that observing the solution, we cannot tell what data we used in the optimization process, right? And this is to address the first part when solution that is released to dispatch problems can reveal what data we used in the process. To address the second part, to improving transparency in power systems, understanding better what the grid is looking like, I'm looking to a problem of privacy-preserving synthetic dataset generation. And the idea is that, okay, the real dataset, for many reasons, many valid reasons, will never be revealed to public, right? But maybe we can, based on this dataset, we can produce some synthetic version of a dataset, such that if we plug it into the same optimization solver, it will produce solution that will be very similar to the solution of the original data. So the idea is that private synthetic data set is the one that generated based on real data, but not disclosed, right? But at the same time, it produces consistent outcomes, optimization outcomes with the real data, right? And all that will be based on the notion of differential privacy. So we'll first talk about definition of privacy, and then overview two works of ours. One is on privacy-preserving optimization by means of stochastic programming, and the second one is on synthetic dataset generation. How many of you worked with differential privacy before, by the way? One? Is it raised hand or you just? Okay, just two of us. Okay. I put some definitions. So let's at least the talk will be successful if at least we build this intuition for that. Okay. So let's define privacy. So we can think of a wind turbine, right? And we can think of wind turbine as a data universe. So at any point of time, a wind turbine will produce some quantity of power between 0 and 1, and we will call it like power record, right? So think of it as a data generation resource. These records are different, right? So our privacy goal is to make two records from this universe, any two records that are in some close proximity one to another, say bounded by alpha, make them look similar, right? How we can do it using differential privacy? The standard approach is to perturb the record to make it look statistically similar to another one. That means that we will take, say, record Y, and we add some Laplace noise to this record. And instead of releasing the real data, we can produce some synthetic version of it, which is Y hat, right? And justification for using noise here is because if you do the same procedure, but for record Y hat, the probability of observing the same outcome Y hat from the distribution induced on the different record is similar. The similarity is measured by so-called parameter epsilon, privacy budget of privacy loss. The definition of epsilon differential privacy says that let's take the measurement, right? And let's apply some noise to this. This is a Laplacian noise that is parameterized by some data-independent parameters, adjacency, that doesn't depend on particular data set, and epsilon, which is our privacy requirement. When we look at the ratio of probabilities of observing the same outcome by perturbing different records, this ratio will be bounded by epsilon, right? And what it does essentially, as long as the epsilon is small, then these probabilities, they're similar, meaning that these probabilities, they're very, this function is very well aligned, right? We can also think of epsilon as some bound on probability distance between the two distributions that are induced on data set. So basically, when we perturb the records and we observe the sample, we cannot tell from which distribution it came from, the one induced on measurement Y or Y hat. Hence, we cannot differentiate between these two records, hence differential privacy, right? And it's a strong notion that owns a lot to few mechanisms. I mean, the success of it owns a lot to two simple mechanisms that were introduced in this area. One of them is Laplace mechanism. So we take a function that maps data set to reals. And let's think of a worst case sensitivity of the function to input data sets. It's basically, we want to find such instances of alpha adjacent data sets that maximize the difference of function value. And this value is independent from particular data set D or D prime. It only depends on the range, right, of your data set universe. And Laplace mechanism works as follows. Let's take our original function and perturb it with Laplacian noise with zero mean and a scale that parameterized by sensitivity and epsilon. And this will give us this result that observing the same outcome y hat from perturbed function on data set D and D prime, like this ratio is bounded by epsilon. And this definition is strong in the sense that it has some very interesting consequences. So one of them is a composition of differential privacy that basically says that if we have a series of computations on the same data set D, then if every computation is epsilon differential privacy, then together they achieve chi epsilon differential privacy. So it's we lose privacy. Basically, what it says is that when we use a data set many times, we will eventually disclose the data over time, right? And another, yeah.
Question: is y hat a set?
Say it again.
Is y hat a set because you have some value in y
yes,
hat?
yes, that's true. The idea, I think, why would you put it this way is to avoid put the exact equals to, because having two functions that equal exactly the same number, right, and continuous is probability 0. So you would reason like about small set y hat. So, for example, think of it as a discrete number for convenience. But it's a good point. I honestly don't know how much in detail I should go to at this point, but yeah, I appreciate the question. Another interesting point is immunity to post-processing. So meaning that if we get our epsilon differential private response and we apply any transformation, right, for this response, we still preserve the guarantee. So meaning that yeah, we can do any data-independent transformations of our privacy-preserving response, and we will preserve the guarantee. Another interesting and relevant for this talk mechanism is called report noisy max. That what it's doing, it's if with Laplace mechanism we respond some numerical queries, right? With report noisy max, we do some non-numerical, enable non-numerical queries. Think of a population of functions, right? And think of a worst case sensitivity for these functions. Report noisy max is a discrete version of exponential mechanism that help us to answer the following kind of question. What function takes the maximum value on a private data set D? We want to get this answer to this question without disclosing data set D. The report noisy max works as follows. So we would apply Laplace mechanism to every function, and we will return the index of the function with a maximum value. And you see, although we made a k computations on the real data, right? We would think of composition that will tell us that our privacy loss scales with respect to k. But because we only release the index as opposed to releasing the entire set of responses, right? Then we only induce privacy loss of epsilon. And it's a very important result and, that we will use eventually to answer the kind of questions. What is the worst case optimization model on a particular data set? In terms of dispatch, what is the worst case operating condition on the for a particular load, right? And we will return to this mechanism later in the talk. But let's discuss how we can enable privacy preserving optimization using stochastic programming. And for that, I'm introducing the conic optimization problem, which is given by a form. So we minimize a linear coarse function subject to a set of conic constraints. And here the data set is coefficient and parameters of the conic constraints. What we know about it, often optimal solution on different datasets differ, and hence we can differentiate between datasets by observing the optimal solution of this problem. And it's also very general. It can be a linear program, it can be a regression problem. As long as it's a convex problem, it can be represented by this form. And if we think of a standard differential privacy approach to solving unconstrained optimization problem, it would look something like this. Input perturbation. So in order to obfuscate the real data here, we would perturb the data with a privacy-preserving noise, and then we will solve this problem on the privacy-preserving version of a data set and report privacy-preserving optimization solution. We can also go for output perturbation method that will compute the worst case sensitivity of your optimization problem to datasets, to adjacent datasets, and then it will compute the optimal solution on a real dataset and then apply privacy preserving noise that is parameterized by the sensitivity of your optimization problem to input datasets. And these two approaches satisfy definition of differential privacy, meaning that you can report solution to optimization problem privately. The problem is that using either of the strategies, the problem is that they don't guarantee feasibility in cases when we need it. And to illustrate this, consider a simple linear programming example where we minimize linear cost function subject to this interval constraint. And the optimal solution to this problem will always disclose the lower bound. Let's take it as a private button, right? When we change L or L prime, this difference is directly exposed in the optimal solution. Using standard differential privacy approach, we would perturb this solution with a privacy preserving noise. And here you see this density functions, these two probability distributions will be close to another, enabling differential privacy, but solution will be infeasible with probability 50%. The question is, how can we ensure feasibility and privacy at the same time? So this is a challenge. And to answer this question, we propose to use, for every deterministic problem of this form, we develop a stochastic optimization counterpart. What it's doing? It inherits the structure, the objective function and set of constraints, but instead of optimizing a single vector of decision variables, it optimizes the linear the linear function of a perturbation. So we have, instead of optimizing vector x, we optimize some nominal solution plus recurse solution multiplied by random perturbation. What it means, when the perturbation is zero and there is no parameters of perturbation is zero, this problem replicates the original problem. But when we anticipate some privacy preserving noise that we will apply to a solution, the solution to this problem will be different. It's structured such that, constructed such that we minimize the expected cost subject to so-called chance constraints. And the chance constraint, what they do, they say that when we optimize this linear functions of perturbation for in the optimal for at least 1 minus eta% of scenarios for random perturbation, your constraint must be satisfied. So it's basically imposing feasibility guarantee for the optimal solution of this problem. What is this variables here? This is called a linear decision rule. And essentially it says that for optimization, essentially what it says, it's a linear decision rule of the following form. It has a nominal component that is dependent on data and has a recurse component. And if you work with stochastic optimization before, you would think of zeta as an uncertainty in your data, right? Uncertainty in renewables when we dispatch power systems under uncertainty. Here, though, zeta is not uncertainty of data. Data is fixed. It's intentionally introduced perturbation. There are different queries that we can answer. One optimization query is called identity query. Basically, what we want to do, we want to release the vector of the optimal solution. In order to release the vector of the optimal solution, we need to make sure that this component is data independent. And to do it, we have additional constraints on our recourse. They require to be identity. So in optimality, when we solve linear decision rules using this chance constraint program, our response will look like optimal solution for the nominal component plus data independent perturbation. And similar for some queries. We introduce other set of constraints. And let's get back to our linear programming example to understand how it works in action. So now, instead of solving deterministic problem, we're solving a stochastic problem where parameters of the perturbation are given by our privacy preferences. We will specify some eta, which is constraint violation probability, and we'll put it small, say it should not violate our constraints with probability at least 95%, right? Then the optimal solution for the nominal vector x bar no longer will be at the boundary of the feasible region, but instead it will be somewhere in interior, the feasible region. And the reason is because when we perturb it with a privacy-preserving noise, we can show that solutions to this problem on adjacent datasets L, Ln prime, they will be statistically similar as per differential privacy. At the same time, we ensure that if we sample a solution from any of these distributions, it will be feasible with very high probability, right? When feasibilities will remain in these tails, right? And this is, long story short, for every deterministic problem, we have a stochastic optimization problem. When we calibrate the parameters of the perturbation enough, we can guarantee privacy and feasibility at the same time. Yeah, just to summarize how it works, this is the main result. So we will have, we need to specify, to enable privacy guarantee, we need to specify dataset adjacency. We need to obtain solution sensitivity to alpha adjacent dataset. And we also need to specify privacy budget. We then calibrate the parameters of this perturbation here to Laplacian noise and solve the stochastic problem. And eventually we can specify definition of differential privacy on optimized linear decision rules. We can say that when this linear decision rule is optimized on dataset D on D prime, probability of observing the same outcome similar up to parameter epsilon. Okay. There are a few applications for that. One of them is privacy-preserving optimal power flow problem. And this problem is solved in power grids to obtain feasible and least cost generator dispatch to satisfy the loads. Load information, we can think of it as a private datum. And we like to solve this problem such that when we make a query, when we ask for some aggregated generation or for system cost for the value of objective function, adjacent load vectors will be statistically similar. So for that, we will formulate the stochastic power flow problem that minimizes expected generation cost where expectations with respect to parameters of the perturbation subject to perturb power balance constraint and chance constraint on network limits. And this table shows the result in terms of feasibility of the OPF solution and suboptimality of the OPF solution with respect to the parameters of the noise. And we have three strategies. First, two strategies rely on perturbing the original data and solving on unoriginal data, or output perturbation solving OPF on the original data and adding noise afterward. And I mean, it's pretty straightforward that will be, we will see infeasible solutions for these two strategies. If we solve a chance constraint program for some choice of eta, we will have a very small violations, the constraint violations when we perturb the optimization query. We also see the trend that when we increase alpha, so universe of data set increases, we like to make more load vector statistically indistinguishable. We increase privacy parameter, it increases noise in the system and induce more suboptimality, revealing fundamental trade-offs between privacy and optimality in this case. And that's how it looks in practice. So what we have we have we depict so the query that we make is in the system cost, and this is a distribution of system cost on 3 different data sets: D prime, D double prime. And epsilon is chosen large, meaning that the magnitude of noise is small. We see that we can clearly distinguish between different distributions, meaning that we don't have much of privacy protection. When we reduce epsilon to 1, we increase the magnitude of noise, and our random system cost on 3 data sets looks statistically very similar, right? So when we observe a sample from this distribution, we cannot tell from which one it came from. Hence, we cannot differentiate between input data sets to our stochastic program. Okay. We also have some other applications here that I think I need to skip in the interest of time. Yeah, maybe I will just report this interesting application to support vector machine classification. So the idea is that we have a data set, and every record in the data set has a feature and corresponding label. We would solve quadratic optimization problem to optimize the classification rule to attribute the point to one class or another. Eventually, we have optimize this boundary. What this boundary tells us, it tells us about the data sets that we use. So we like to perturb this boundary with some privacy preserving noise so as to obfuscate data. We can perturb the deterministic hyperplane, or we can perturb the stochastic hyperplane that is obtained by solving a chance-constrained counterpart of the original quadratic program. And what you see is that this is the average solution. This is the nominal solution for hyperplane. And you see that in stochastic setting, it's suboptimal with respect to that obtained from the deterministic solution on the original data. So it's less accurate, but for a good reason, because when we perturb these 2 hyperplanes with privacy-preserving noise, we will see the following behavior. These gray lines, they depict random realizations of a hyperplane when we perturb parameters. And we see that the deterministic hyperplane is very sensitive to perturbation. Its classification accuracy drops radically. But when we perturb stochastic hyperplane, we see that it's a very robust to perturbation, meaning that we can release the classification rule that remains close to the mean value, right? That classifies pretty well, but at the same time doesn't disclose the data set, right? And in application to power systems problems, we took a standard test case. We took a vector data set with where feature is a vector of loads, and the label will tell whether it's feasible for the system or not. And this is SVM works very well in this case, so we have a high classification accuracy. When we use output perturbation method on solution of deterministic SVM, the accuracy reduces, as we saw before, and it also has high standard deviation. But the beauty of chance constraint solution is that, okay, let's fix eta to 5. So we will allow for constraint violation only in 5% cases. What we can see is that it significantly improved the classification accuracy, has some standard deviation, but it's not as high as a non-private classifier. But when we reduce the eta, we see the trend that we significantly improve accuracy, and eventually we can almost match the accuracy of the non-private classifier in some small standard deviation and provide privacy at the same time, right? Okay, in the next part of the talk, I will talk about, yes?
So you're focused on constrained optimization problems. What if you have non-constrained?
So for non-constrained, you can solve this problem, but there won't be constraints, right? So it's
you need the constraint, right?
For this framework, yes. So we need for unconstrained problems there exist iterative algorithms like gradient descent and privacy preserving version of a gradient descent. What it does in unconstrained problem, it perturbs the gradient at every iteration, and use composition with threshold privacy to bound the privacy loss of iterations of the algorithm. That's what you do for unconstrained optimization. But it won't work when you have a constraint and when your constraints involve private information. So you need something else. And this is exactly the case that we address, constraint optimization problem.
How does it, I mean, I assume for some problems, like you have an unconstrained problem, but you can write it as an equivalent constraint. With the SVM, you can write that as an unconstrained problem.
Yes, that's
So
true. That's true.
So you've got two different approaches.
Yeah.
Privacy preservation.
Yeah.
Is one preferable?
I didn't think about it. Honestly, I don't have an answer right away. So it makes sense for me to compare. It's just we were thinking of a conic optimization problem of this form, which is general, right? So if you solve this problem for conic problem, you can similarly address linear programs, quadratic programs, semi-definite programs, right? That was our starting point. So that we were thinking of generality, but I agree that yeah, there are more to look at.
Is there a direct connection between epsilon and eta?
Yes, there is. A good point. So eta is your feasibility preference, and epsilon is your privacy preference, right? So what happens when you reduce epsilon? You increase the magnitude of the noise, right? What happens when you reduce eta? You shrink the feasible region for the nominal solution x hat. So meaning that if you have too small epsilon and too small eta, you have too much noise to accommodate in a very small feasible region. Solution to this problem will be infeasible, meaning that you cannot provide, using this framework, you cannot provide required level of privacy at a required level of feasibility.
So is it like closed form or?
No, there is no straightforward solution. There is no straight connection between eta and epsilon. So you won't be able to express your privacy guarantees in terms of epsilon. Oh, in terms of eta. In terms of eta. Yeah, we still have between 15 minutes to cover synthetic dataset generation. So this is a problem that of generating high quality synthetic datasets from the real datasets that are out there in the real world. So it's not a new problem for power systems because again, these infrastructures, they are very sensitive and we don't know exactly the topology or parameters of transmission lines or generation mix or load information. But the community was creating some synthetic data sets that would represent some version of United States power grid or that in Europe or in Australia. The punchline here is that when you look into the description of this, they often would claim data bears no relation to the actual grid, it's fictitious transmission, or it doesn't model the actual grid. And there is a reason for that, because you don't want to be responsible for disclosing real data. So the authors really want to put this disclaimer to avoid any legal consequences for that, right? But at the same time, it's kind of, we feel sorry. So we have an actual infrastructure, but the data that we have at hand doesn't explain it very well. So what we want to do, we want to generate high quality synthetic version of the real data. And we can use differential privacy for that. I will talk about two algorithms to do it. One of them is for wind power obfuscation algorithm. So what it's doing in this setting, we have a wind power generation records as a data set of n records, where we have a wind power measurement y and some feature like a weather, wind speed, or wind direction. So what we like to do, we like to produce synthetic version of a data set where the power measurement will be synthetic, denoted by tilde, and that will correspond to the same public feature that is known to everyone. Using Laplace mechanism, straightforward approach is just to perturb the measurements, power measurements with a Laplacian noise and get your synthetic data. The problem is that the record might go outside of generation limit of a wind turbine, and it might lose important properties like regression analysis on synthetic data set will not be the same as that on the real data. So for that, what we like to do, we like to ensure that the synthetic data is consistent with respect to the real data, with the real data with respect to regression analysis outcomes. And the outcomes, we will think of the loss and the weights of some regression model. We can, yes.
I have a question. Is that, I mean, the condition would be, like if you work for MISO or some project and the company gives you a data set, and you doubt it is not real.
Yeah, that's so when do you need to use this algorithm, basically, right? Do you ask it? This is all private companies that produce wind power, right? So they won't release the real data for the reason that it will disclose many sensitive information. For example, the manner that they operate their wind turbine, right? So or some operating conditions on the wind turbine, right? Or how they handle icing and stuff like that. Because all this information can be inferred by looking into power measurements, right? So I doubt that you as a researcher, right? Or you as a, I don't know, machine learning engineers that like to train the best machine learning model, I doubt that they will reveal real data. And hence you would use this algorithm to produce some synthetic version of it that is consistent on the regression analysis.
The thing I'm worrying is that it's like actually there would be some noise in the data and we have to get rid of them. But I mean, the results would be after we use differential method, it's like the prediction would be accurate or more perfect. But I mean, that's it real work. Good. Thanks for bringing the skepticism. It's always good to see. I will show it to you. Okay. Yes, there will be. So basically, what we are doing, we take a data set, we perturb this data set, and then we will use optimization-based post-processing to restore important properties. And this properties includes, here we have a fixed regression model, and we like that the regression weights on the real data and synthetic data will be similar. We also like that the regression loss on synthetic data set or real data set will also match. Then you can take more information from your regression outcome and try to post-process your synthetic data to match this performance of a synthetic data set in terms of the same analysis as you do on real data. For that, you need private estimates of loss. Okay, I will have to skip it now, but that's how the algorithm works. So you take the real information, you apply privacy-preserving noise. As a second step, you have a set of parameters that you want to estimate on real data, but because you do these estimates on real data, you also add noise in order to obfuscate the data that you use. And then the step 3, that resolves your concerns. What it's doing, it defines synthetic data set as a variable to optimize, and it bounds it within the meaningful limits. And at the same time, when it optimizes, chooses the synthetic data set, it wants it to meet the private estimate of regression loss on the real data. And also the weights of the regression model on the synthetic data should also match the weights on the real data. And this is a regularization parameter that basically says that if initial perturbation doesn't violate much of weights or loss accuracy, then just stick to the initial choice. And this is hierarchical optimization because in upper level, we have a variable of synthetic data set as a variable. And in a lower level problem, we have another optimization, which is a regression model, right? That will take the synthetic data set as input and compute the loss and regression weights on synthetic data set, right? And then it will give feedback to upper level problem that tries to match weights and loss.
And is the lower level problem ridge regression with 2 norms squared that you're just sort of not showing the 2s, or
I'm not showing the 2s. I'm not showing the 2s. Yes.
So it is linear. The lower level problem is linear then.
Yes. It's a linear problem.
It exists closed form solution, so we replace it with closed form solution. It's a linear constraint, but sharp observation. Yeah. And basically, so you see in this algorithm, we apply, we use real data set several times. The first step and at the second step twice, right? So we need to account for it when we give privacy guarantee. So we use composition differential privacy to scale parameters epsilon at every step, to which we guarantee epsilon differential privacy with respect to how many computations we made on the real data. That's how it looks. So we have WPO algorithm on the right. We have Laplace mechanism on the left. So crosses show real data, circles synthetic data. We have a regression model as a reference. And now I will show you animation where we will solve, we just apply noise to data using Laplace mechanism as a simple baseline approach. And this algorithm will also apply noise to data, but it will use optimization-based post-processing. And adjacency alpha will vary. So alpha is 1%. We want to make any record that is distinguished between 0.01 range from each other. It's a small parameter, but now we will increase the amount of noise and see what happens. So when we just apply increase alpha, we increase noise that we perturb data with. No surprise, Laplace mechanism will result in a data set that lose completely touch with reality, right? But because we use optimization-based post-processing, our synthetic data set will remain very close to the original data. Again, we perturb it, but we also restore its regression performance with respect to real data, and hence records stay very close to each other. So when you go to the operator of wind farm, so maybe they won't give you real data, but you can ask them to produce synthetic measurements using this way, right? And the second algorithm is for transmission system obfuscation. So we have this graph, we have transmission lines, where capacity of transmission line is a very sensitive information that is not available to us. The question is how we produce high quality synthetic version of it. For that, we need a reference optimization problem, which is an optimal power flow problem that basically takes information from the grid, like cost, demand, transmission capacity, and maps it into cost optimal dispatch. This problem is solved daily in the practices of system operators, and this parameter is unknown to us. So we want to produce synthetic version of it using this problem as a reference for quality of synthetic data. So first baseline approach, Laplace mechanism, take original data, perturbed with Laplace noise, might not be feasible. Okay, idea from our colleagues from Georgia Tech, let's take this perturbed value and post-process it, treating synthetic data set as optimization. And here we have a constraint that OPF cost on the synthetic data and the original data, some estimate, will be similar, right? But also by virtue of embedding an OPF problem as the problem in the constraint set, it's also a hierarchical optimization problem. You also guarantee feasibility for your synthetic data. The problem here is that this approach works well for instance of an OPF model for a fixed value of demands or generation parameters. In the real world, we have system parameters varying, demand change all the time, wind power generation change all the time. So we need a synthetic data set that will be feasible and cost consistent with respect to population of different operation conditions. And for that, that's why we use Laplace and exponential mechanism. And think of it as a report noisy max that I was referring to at the beginning of the seminar. So what we will do, we will obfuscate data as usual. Then we will find the worst case OPF condition where the cost and feasibility on original data and synthetic data is the largest. And then we will run post-processing by level optimization on the worst case model. And the hope is that if we run it on the series of worst case models, we will perform well for the entire population. Right? Let's look with a bit more in detail. I will try to wrap up in a few minutes. So we perturb data, we find the worst case operating conditions where synthetic data set and real data set differ the most. We then compute a private estimate of the cost on the real data for the worst case model. And then we run a post-processing by level optimization that optimizes synthetic data set, ensures feasibility and cost consistency with respect to worst case model. And we repeat the steps several times to find cost consistent and feasible synthetic data set on a T amount of OPF problems. This is difficult problems to solve. This is embedded linear programs. We end up solving large-scale mixed integer program, quadratic mixed integer program to solve it. We also guarantee privacy. And this is a result, basically. So what we're doing on the left, it's a Laplace mechanism. These blue bars show you the sorted real transmission line capacities. And the maze bars show you outcomes of a standard Laplace perturbation. The one on the right, it uses pretty much the same noise as in Laplace perturbation, but it also post-processes it. And after a single iteration, you see that your synthetic measurements are close to the real one, but they're still not disclosing them exactly, right, up to our privacy parameters. But it's only after one iteration. They're still infeasible with respect to 98% of other operating scenarios, and we have some cost deviation. But having this iterative algorithms that I showed you before, we pick selected lines and we adjust transmission line capacity to restore feasibility with respect to entire population and also improve its cost consistency. Okay, I think I need to stop at some point. Okay, just the whole point of this last talk part is to say that, okay, now we can make a synthetic data set and provide the following statements and back them up with the rigorous algorithms. We can say that this synthetic data set is produced based on the data from a real world power grid. That's intention. We can say that it's not possible to infer real data from this synthetic data, right? Because we have formal privacy guarantees for that. And we can also guarantee consistency of how the data set behaves on the same analysis that is done on the real data. And this is our path to impact. Okay, I think I'll stop here and yeah, thank you for your attention, and I'll be happy to take a few questions.
Thank you for sharing your work on differentially private optimizations. And I'm just curious, that could you please go back to page 13? Oh, yeah.
13 is missing.
When the tail of the distributions goes to the infeasible part,
yeah,
do we just truncate it, or
no? It just let's call it bad luck. So that's where your response just doesn't satisfy your constraints. What you would do in that case, you would. I was thinking of resampling, right? Because probability of ending up in the tail is very small. So in that case, you would resample, you will report the other answer, but at the same time, you will degrade privacy because you will do another computation on the real data. So you will lose privacy guarantee. So you would have to divide epsilon by 2, multiply epsilon by 2. So that's what I would do. For truncated,
is it like we keep resampling until it's indefeasible?
Yeah. But every resampling will degrade privacy guarantee that you have, right? So it will be weaker guarantees that you can give to that outcome. But yeah, the hope is just that the density is very small. This, the probability is very small for returning feasible sample.
And for X star, the left side of it, the yellow region of it, is smaller than L. Is it going to be a problem? I mean, the feasible set is between L and U, and if we goes to a small value like L bar, it would be smaller than L. Is it acceptable?
Can you repeat the case again?
I mean, I thought the feasible set is between L and U, and
yeah, on dataset L, right? On dataset L prime, it will be different feasible set, right? It will shift, right?
Yeah, and for the resampling region, do we still do L, or we do L prime?
It depends. It depends on what data set you're reporting the answer to. So your feasible region is built on private data. You want to obfuscate it, right? So to report your private answer, you will use a regional, the feasible region that pertains to your data. So if you optimize on L, you will basically, you have this region, you will sample from this distribution, right? Induced on a record L, right? And yet there is some probability that it will be infeasible. If you optimize on L prime, you sample from this distribution, right? And yet there is also a probability that it will be infeasible, but the infeasibility now defined by the feasible region that built on L prime. Okay.
So no questions next. Thank you. It was a great time.
Excellent. Thank you. Thank you, everyone. You saved me.
Can I just ask some more follow-up questions? I've been working on different purposes, specifically for decentralized system.
All right.
And